The Northern Lights, a scientific exploration of the Aurora Borealis. The Northern Lights, scientifically known as the Aurora Borealis, are one of the Earth's most remarkable natural wonders. Visible primarily in high-latitude regions near the Arctic Circle, these glowing lights appear as moving curtains, arcs, and waves of colors across the night sky. While they have inspired legends for thousands of years, modern science has revealed that the aurora is the result of complex interactions between the sun and the Earth's atmosphere. Understanding the Northern Lights begin with understanding the sun. The sun and solar activity. The sun is not a calm or constant star. It continuously releases energy in the form of light, heat, and charged particles. These particles, mainly electrons and protons, flow outward in what scientists call the solar wind. At times, the sun becomes especially active. Solar flares and coronal mass ejections can send enormous clouds of charged particles into space at extremely high speeds. When these particles are directed toward Earth, they can reach our planet within 1 to 3 days. Without protection, the solar radiation would be dangerous to life. Fortunately, Earth possesses a powerful defense system. Earth's magnetic field. Surrounding our planet is an invisible magnetic field generated by the movement of molten iron in the Earth's core. This magnetic field deflects most charged solar particles, forcing them to flow around the planet rather than strike it directly. However, the magnetic field is weaker near the North and South poles. In these regions, some charged particles are guided downward along the magnetic field lines and into the Earth's upper atmosphere. This is where the aurora is created. How the aurora forms. When high-energy particles from the sun collide with gases in the Earth's upper atmosphere, primarily oxygen and nitrogen, energy is released in the form of light. Different gases and altitude produces different colors. Green is the most common color and is produced by oxygen at low altitudes, about 60 to 150 miles above Earth. Red auroras occur at higher altitudes and are also caused by oxygen, though they are rare. Blue and purple colors result from the interactions with nitrogen. These collisions do not produce heat or fire. Instead, the process is similar to how neon lights glow. Atoms become excited and release energy as visible light. While the lights move. One of the most striking features of the Northern Lights is their motion. Auroras can appear to ripple, pulse, or wave across the sky. This movement occurs because the Earth's magnetic field is constantly shifting in response to changes in solar wind pressure. As the magnetic field adjusts, streams of charged particles follow new paths, creating the appearance of flowing lights. Aurora displays can change shapes in seconds or remain steady for hours, depending on solar conditions. Where and when the Northern Lights are seen. The Northern Lights are most commonly visible in regions called the Aurora Oval, which forms a ring around the magnetic North Pole. Countries within this zone include Alaska, Northern Canada, Iceland, Norway, Sweden, Finland, and Greenland. During periods of strong solar activity, auroras can expand far southward and can be seen in places such as the northern United States or Central Europe. The best viewing conditions include dark skies away from city lights, clear weather, late evening to early morning hours, and increased solar activity. Auroras occur year-round, but they are easier to see during winter months because nights are longer. Solar cycles and auroral intensity. The sun operates on approximately 11-year solar cycle, alternating between periods of low and high activity. During solar maximum, the most activity phase, auroras occur more frequently and are often brighter and visible farther from the poles. During solar minimum, displays are less common and usually confined to high-latitude regions. Scientists closely monitor solar activity, using satellites to help predict when strong auroras may occur. The effects on technology. While beautiful, intense solar storms that causes auroras can also affect modern technology. Strong geometric storms can cause disruption in satellite communications, interfere with GPS signals, affect radio transmissions, cause power grid disturbance. For these reasons, space weather forecasting is an important field of study. Monitoring auroral activities helps scientists protect technology and infrastructure on Earth. Scientific importance of the aurora. Auroras are not only visually impressive, they provide valuable scientific data. By studying auroral activity, researchers gain insight to solar behavior and solar storms, Earth magnetic field dynamics, atmosphere chemistry, space weather patterns. This information helps scientists better understand how Earth interacts with its space environment and how similar processes may occur on other planets. Auroras beyond Earth. Auroras are not unique to our planet. Scientists have observed auroras on Jupiter, powered by its strong magnetic field and volcanic activity on its moons. Saturn with its massive ultraviolet auroras. Mars, which experiences localized auroras despite lacking a global magnetic field. These discoveries show that auroras are a universal process wherever magnetic fields and charged particles interact. Conclusion. The northern lights are the visible result of an ongoing relationship between Earth and the Sun. A reminder that our planet exists within a dynamic and energetic solar system. What appears to be a silent light show is actually a powerful scientific process unfolding high above the atmosphere, shaped by forces that begin nearly 150 million kilometers, or 93,205,678.8356 miles away. By studying the aurora, scientists not only learn about the sun and Earth, but also about the fundamentals interactions that govern space itself. The northern lights stand as one of the nature's most vivid demonstrations that even in darkness, science can illuminate wonder.